Welcome to Lesson 4,
Speed time graphs.
Velocity Time Graphs.
Almost the same thing. Velocity or speed time graphs pretty much will share all the requirements of our DT graphs, our distance or displacement time graphs. There's only going to be a few differences in terms of what we can do. Other than that, watch for your units, watch for your directions. Here's the graph.
Figure 1, Aubrey and Ollie running away from home in a dog-pulled stroller.
Before you ask, that's what it would look like. If this was the olden days, it might even... Oh, wow, that went really forward. It might even look like new versus old. Now, this is our graph of Aubrey and Ollie running away from home in a doggy-pulled stroller. What do you notice? Oh, we can't move this thing. There we go. We notice that we still have all of our axes labeled. We still have a title. Our data has not yet used half of the graph. That's bad. But the reason it hasn't is because we're going to add stuff to this later. We have a scale. It's uniform. It's 1 decimal place on the bottom. It's 2 decimal places on the left. Everything seems to be okay there. So, some questions that we could ask you about this. What is the velocity of the stroller?
So the first question you should be asking yourself with this is the velocity changing? As we take a look at the graph, we can see as we're going across, nothing is changing. We don't see a slope. We don't see anything like that. So we are keeping a constant velocity.
The other thing to note is this is not a displacement or distance graph, so you don't have to calculate it using slope. The left side says velocity, so read the graph. What is the velocity?
Okay, and again, since we're reading the graph, all we would say is 7 kilometers an hour, since nothing's changing.
Now, this is the question of, is the velocity of the stroller changing? Well, we can say no, but we have to also be able to look at this and say, how do you know? Prove it.
Okay, so again, if you really want to prove this, we would just take a look at the top of the graph. We would see and do our slope calculation, because that's what we do when we're trying to find change in a graph. We go rise over run, and now we end up seeing, just due to our rise, we would see 7.00 minus 7.00 divided by whatever, because we already know that this is going to equal 0 over something, which is just 0 anyway. So if our slope is 0, we know that the velocity is not changing.
Slope is rate of change. Whoop. Last thing we can ask. Now this we didn't see in a DT graph. Well, actually, I guess we did. You just read the graph and it was easy. How far from home did Aubrey and Ollie go? Well, we're looking at a VT graph. This tells us their velocity. We can also see their time. So, ladies and gentlemen, there is something called area under the graph. Essentially, if we turn our graph into one big rectangle on a velocity time graph, this should give us displacement. Let's double check. We have 7 kilometers an hour, so 7 kilometers per hour represents our base length times our height. The height here is, the height was 7 kilometers. The base is along here. It is the 0.8 hours. 5.6 kilometers. So area under a VT will always give us D. Now, there's another way you can actually start to look at this too. Some people will say, well, can't I just take a formula and rearrange a formula? V equals D over T. D is equal to V times T. Well, that's essentially what this is. Here is V, here is T. So, why would we tell you that you have to do the area under a graph if you could just use a formula? Here's that other section of the graph we mentioned.
So now we take a look at, obviously, we see the exact same thing we had before, okay, with an unchanged velocity. Okay, but now we're adding in a section here where obviously we see some slope. Okay, with the slope section now, again, this is where that area under the line becomes very, very important, because now, again, we have a slope calculation to find. Velocity is not staying constant, so now it adds a little bit more difficulty to our calculation. So this is the same graph. We just added a section, as we mentioned before. What's happening to the velocity of the stroller from 0.8 to 1.2 hours? So again, we have 0.8, 1.2. From this section, what do we notice? Take a second to think about it.
The velocity goes up.
Again, at this first section, we have roughly about 7 kilometers an hour. And up here, we're all the way up to 19 kilometers an hour. So we know velocity changed over a given time period.
It's pretty good. 19 kilometers an hour. That dog's moving.
I know. That's not messing around.
Now, what is the actual rate of change? So as soon as it says rate of change...
And make sure you say rate like that.
We want to find slope. So that means that we need 0.2 minus 0.1. Y2 is 19. Sorry, I guess I could write it. Y2 minus Y1 over X2 minus X1. We want 19.00 minus 7.00 kilometers per hour divided by 1.2 hours minus 0.8 hours. This will give us 12 on the top and a 0.4 on the bottom. 12 divided by a 0.4 is
30.
30. What are the units? Oh, they're kilometers per hour per hour. That looks kind of goofy. Let's just say that it's kilometers per hour squared. So, this represents how fast the speed is changing. Some of you might already know that how fast speed changes is something called acceleration. This is actually the topic of the next lesson, so we're not going to go in depth on it. We're just going to go back to what we're trying to get you to learn on a VT graph.
Okay, how far have Aubrey and Ollie gone from 0.8 to 1.2 hours? Now, what we're taking a look at, just like last time, we are going to use the area under the line. Okay, so we're going to split this up. Obviously, if we take a look at this full area here, it is a very weird looking shape. Okay, but there's nothing saying that we can't break the shape up into simpler things that we know how to use. So we're going to use the area of a triangle, which is 1/2 base times height, and we're going to use the area is equal just to base times height, or the length times width, however you want to think about it. So if you take a look, we got 1/2. Okay, our base here is 0.4. Okay, on the bottom, our height is 12 kilometers an hour, and we get an answer of 2.4 kilometers.
But that's not all.
Now we have to solve the second part in order to find the total distance. So we'll call this part 1, we'll call this part 2, and at the very end we add 1 and 2 together. Okay, so for this area here we're going 7.0 kilometers an hour times 0.4 hours gives us 2.8 kilometers.
So our total, if we take our 2.4 and our 2.8, is that we are going to have a distance traveled of 5.2 kilometers. Now, why did we do the area under? Well, in this one, ladies and gentlemen, if you try to rearrange your formula, unfortunately, there's a whole bunch of different velocities. Through here, through there, velocity is constantly changing, so which one do we use? We use the graph. That's easy. Now, the one thing that would be interesting to note here is a question like this now asks how far have they gone after 1.2 hours? So that's not asking for the little segments. How do I find out how far they've gone after 1.2 hours? Well, I will take the area all the way to 1.2, break it into little sections 1, 2, and 3, and then I know that I have my 2.4 from before, my 2.8 from before, my 5.6 from before. This is equal to 10.8 kilometers.
In what direction?
Oh, good point. 10.8 kilometers is a distance. So now, in order to put a direction on this, I come back to here. This is a way. The other thing to note, ladies and gentlemen, if you ever see a graph like this, and for some reason the line actually happens to dip down below 0, anything down here, you're still finding the area of. The only catch is that here, your area should be negative. And then you would still add them all up.
And you're just making that area to the 0 line, not anywhere above it.
Just go back to 0.
Looking at a distance time graph, you can find the rate of change of position, speed, or velocity by using the slope. Obviously, this doesn't change from before.
For our VT graphs, you can use the rate of change slope to now find acceleration. So it's like we're upgrading every single time.
By looking at the unit analysis, we see the area under line on a VT graph gives us the following. So if we take a look at all these wonderful structures here, we end up taking a look at the area is equal.
Well, area can be distance or displacement. Doesn't matter. It's equal to base times height. This essentially means that we're always going to have something like kilometers per hour times hours giving us kilometers. Or we're going to have meters per second times seconds gives us meters.
Just pay close attention to the units. If velocity's in there, the direction carries over too. The area under the VT graph goes back to distance and displacement.
Speed gives you distance. Velocity gives you displacement. Just watch the directions.
If the VT graph is made up of multiple lines that are different, we break that area underneath into little segments and we calculate each segment like we showed you. And then we just add them all together. We all know how to add. We're all good.
And it doesn't matter if they're positive or negative. Add them all together. Done, done, done. That's all.